My custom chocolate mold starts here with a CAD model. Here I have a simple block with a raised edge. This edge will hold and retain the silicone that will pour into this block once it's been machined. Well, we want to actually make something, so the next step is to actually add our individual items. So I start with a simple block. This is the general shape of the chocolate piece that I want to cast. Next, I chamfer the edge. This does two things. It gives a little bit better look to the chocolate that we're going to be casting out of this, and the breaking the edge makes it a little easier to demold the chocolate when the time comes. Then we add the logo. This is the logo for Inman Perk Coffee, which we'll be cutting into these blocks. The actual cut of this, the recesses here, is not very deep at all. It's only 1/32 of an inch deep. You want to try to avoid exceptionally deep recesses in your mold. And actually, this is the finished part. This is a positive. So when we go to demold it, if you have a very deep recess, especially if it's really small, like these areas over here, it's very, very easy for something like chocolate to break apart when you're demolding it. So we have a very, very shallow recess. And this is the shape that we want. This is the individual chocolate piece that we want. But since we have more space inside of this block, we can replicate this pattern on 2 axes to give us a total of 5x2 or 10 blocks for this particular model. Once we pour the silicone in, we will have a negative that will allow us to cast 10 of these chocolate pieces at once. Once you've gotten to this point, you can either go on to CAM, which is what I'll be doing, and machine it yourself, or you can export this file and send it off to another company that would machine this positive pattern master for you. Or you could export it as an STL and 3D print it. Now, this particular model is 9 inches on its longest axis, which would be pushing it for most consumer home-based 3D printers. However, you could always send it off to one of the many companies that 3D prints models from STL files, and then you could pick up the process from there. But for me, I'll be going on to CAM next. The next step for me is taking my model into a CAM package. Here I'm using Sprute Cam, which is a CAM package distributed by the same company that sells my mill, Tormach. This is fairly simple. There's only 4 operations. First up, a 1/4 inch cutter comes in and removes a great deal of the material, the majority of it in fact, and all of the material around the edges. But the space in between the individual blocks is too small for the 1/4 inch cutter to get in. So the second operation, a 1/16 inch cutter comes down and takes care of those in-between spaces. Thirdly, a chamfer bit comes down and puts our 45-degree chamfer on each block. And lastly, a 1/32 inch cutter comes down and cuts the relief of each of the individual feature elements of our blocks. Once everything's in order, we can come over to the simulator. In this particular case, the simulator is reporting some erroneous errors. But that's all right. But we can come and verify that the cutter isn't going to accidentally impact any part of our workpiece we don't intend to cut. And we can speed it up, slow it down. But this is the path the machine will actually take when it goes to cut. This particular package has the ability to render the machine as well. I render the machine, though, the part is not held still. The camera is held still, and the part moves on the machine itself. But once you verify that everything is good, we can go ahead and export our toolpaths as G-code. And we'll take the G-code over to the mill and actually have it cut this pattern master out for us. The material I'm milling this pattern master out of is RenShape 450. It is a polyurethane composite material. It's pretty awesome stuff. It's unlike wood, it doesn't have any fibers in it, so when you cut it, it doesn't leave any fuzzy bits sticking up that get in the way of your mold. And it machines really well. You can actually machine this or work it with conventional woodworking tools at conventional woodworking tool speeds. However, unlike other composite wood products or natural wood products, it doesn't produce any objectionable dust. It doesn't make sawdust. It does have a downside, however, and it is kind of expensive. Also, it's generally only sold in very large sheets. This particular sheet that this part was cut from is 2 inches by 20 inches by 60 inches. And that part costs about $250, and that's if you go pick it up yourself. Having that size object at that weight shipped is quite expensive. However, this particular piece that we're using is much smaller. Here I'm adding the second part to the silicone with a pipette. You might recognize these from possibly chemistry class. These things are great. They're basically giant syringes, except the part that actually has the pump that pulls the material into the tube is separate. So you can put it on the pipette or take it off. It's a pipette pump. Because the actual pumping parts never come into contact with the material because they're separated by a very long section of glass, you don't have to worry about contaminating the pump and its various sealing surfaces. All you have to do is clean the glass portion. The only exception to something like this is when you are using sometimes some corrosives, if there's a fuming corrosive, which actually the gases from the corrosive can travel up the tube and contaminate your pump. This is much cleaner than pouring the second part into the silicone. This particular silicone mixes 100 parts part 1 to 10 parts part 2, which is really just 10 to 1, but we're adding so little of the second part, it's really difficult with batches this small to accurately add our second part in. The pipette fixes this problem. There's no difficulties whatsoever in adding a very, very exacting amount as it slowly leaves the pipette, goes into the mixing cup, and we read off the gram scale exactly how much we've added and how much more we need. Before measuring out this silicone, I actually used my CAD model to determine the volume of the cavity that I needed to fill. Knowing the volume and the density of the silicone once it's been activated, you can determine how much by mass silicone you need in order to fill the cavity. Now, you'll always need more than that because you'll always have some silicone that is stuck in your mixing containers. I actually know that for this particular mixing container I'm using, that the waste of this particular kind of silicone is about 30 grams. So I take what I know I need to fill the cavity, add my waste, and a small amount extra in case something drips. Like most silicone resins, there is a colorant added to one of the parts. This assists you in visualizing when the parts have been thoroughly mixed. Now, even if it has been completely mixed, it's possible that if you pull your stir stick out and let the silicone run off, you might notice streaks that look a little lighter than the other parts. This is because the silicone is somewhat translucent, so it isn't necessarily that they haven't been thoroughly mixed, but rather that the silicone has become so thin in one area that it's letting more light pass through and therefore looks brighter. The silicone I'm using here is Smooth Sil 940. It is a platinum curing, food-safe silicone. The amount I'm mixing up here is worth about $7. Once the silicone's been mixed, it needs to be degassed. Ideally, we would pour this activated silicone into our pattern and then degas it, so that the degassing takes place in situ in the mold. Unfortunately, I don't have a large enough vacuum chamber to accommodate that, so I will be vacuuming down the silicone in its mixing container and then attempting to carefully pour that silicone into our pattern without adding additional air. This particular mixing container can't hold the volume of silicone that will occur when if we start drawing the air out too fast. So rather than applying full vacuum, I only apply partial vacuum for a period of time. Then once that air, some of the air has escaped, and the volume of that inflated silicone has decreased somewhat, I increase the vacuum. I steadily do this over time until I have a full vacuum applied and I'm removing all the air that the pump can. You can think of this as analogous to the process of firing clay. You are trying to remove water from the clay, but if the furnace is too hot, you remove the water too fast and cause the clay to break. So much as a kiln would apply gradual heat, here we're applying gradual vacuum, though really it's a limitation of the parts that I happen to have available. The cure time for the silicone is 24 hours, so we will let this sit here overnight. Because this is a food-grade silicone, it has additional instructions. Once the part has completely cured over 24 hours, it needs to be baked in an oven or similar vessel for 4 hours at 212 degrees. After this, it needs to be washed with conventional soap and water. Once that's done, it's ready for food contact. Our last step is to test out our new mold. Chocolate is melted in a double boiler, and then when the chocolate's around 90 degrees Fahrenheit, it's poured into the mold. This particular mold is thin enough that it can't support the weight of the chocolate in it without bending a bit, and I would prefer that the chocolate not be disturbed while it's cooling, so I've placed a small board underneath it. A few things to note about the silicone. Silicone's not the greatest conductor of heat. Because of this, when you pour your chocolate into the mold, if you have very thick sections of silicone, those sections will tend to insulate and keep the chocolate warmer for a longer period of time. While this might seem advantageous, because you get more time to work the chocolate into all the corners of the mold before it solidifies, it could be a problem if you were using this mold in a production environment, like let's say a coffee store. Ideally, you would like to be able to get the largest number of units out of the mold as possible. So you would like the material to finish its business in the mold, in this case cooling down so it can be demolded, in the shortest time possible so you can get the next batch going. While you can always make more copies of the mold to get more items per unit time, that means that you have to have more copies of the mold. You may not have space in your facility, or if you're refrigerating these to speed up the process, you may not have an unlimited amount of refrigeration space. So the faster we can get our business done in the mold and the parts demolded, the better. Once the chocolate's poured, I put it in the freezer to speed up the cooling process. About 30 minutes later, the chocolate has actually gone all the way down to freezing. And now it's time to demold the chocolate. This is fairly straightforward. Since the silicone's very, very flexible and this particular mold is not extraordinarily thick, we can bend it and stretch it and get the individual pieces out. And here is our finished item.